Hello, everyone. My name is Dr. Clement Chumesi, and for those who don't know me, last week I did an introductory video on starting a particular lecture series on how to determine the minimal sample size that is helpful or useful to be able to detect an effect or a difference in your study if they truly exist. And we said the software we're going to use is called the GPower software. So there's a whole video on the introductory session that is basically trying to give the scope of the whole lecture series. So if you've not watched that video, please find it in the YouTube description of this particular video. And there's also a whole video, YouTube video on how to install the GPower software, which is going to be the main statistical software for this particular lecture series. So today is just going to be the first lecture series. So we are going to learn how to use the software to do power calculations and so on and so forth. Now, but before we go on the software, so don't forget that if you've not installed the software, that is the GPower software, you should watch my previous video, which is also going to be attached to the YouTube description. So you're going to find the introductory session talking about the whole scope of the lecture series, as well as a video on how to install the GPower software so that you can follow at your own pace. And then I believe that though you'll be exposed to the software, there are other statistical rationale that you would also learn in the course of my presentations as well. So before we go on to using the software, what's the whole essence about power calculation and sample size determination? Now, in statistics, mostly what we tend to do is that we want to answer some research questions. And this research questions sometimes also motivate something called research hypothesis. And by research hypothesis, there are two particular alternating hypotheses, or let me say two contradicting hypotheses that we often are looking into. So we have something called the null hypothesis that basically says that there is no effect irrespective of the kind of analysis you're trying to do. The null hypothesis is basically saying there's no effect. And then the alternative hypothesis is basically saying that an effect exists. So I'm just saying this on the basis of assuming that the goal is to detect some effect if it exists. And the effect could be mean comparison, it could be comparing medians, it could be even comparing correlations, it could be even regression coefficient, trying to test whether those regression coefficients are significant from 0 or not, in essence, to check whether a certain maybe predictor is significant in predicting an outcome. All involves using statistical hypothesis testing. So I just want us to break down. We have very complex hypothesis, but for the sake of this presentation, let's assume that our null hypothesis is that there is no effect. And then the alternative hypothesis is that there's an effect. So keep in mind the effect could be anything, as I've already mentioned. But why is it appropriate and why is it even advisable to determine sample size? If we have unlimited resources, can't we use a very large sample just to perform an experiment or to perform maybe a clinical trials or to perform any study of interest? Because if you think about it, we always believe that large sample is always a good thing, because the larger the sample size, of course, we believe that you have higher power and so on and so forth. But before everything, let me try and explain some few terminologies so that we would all be on the same page. So now, when we talk about the null hypothesis in research, is often that is just a statement. It's just a statement whose validity is of interest. Okay, so it means that it's a statement which could be true or false, and its validity is of interest to us. And alternative hypothesis is always that statement that we assume to be true when a null hypothesis is rejected. Now, there are two major errors that are attributed to hypothesis testing. So one, there are instances where the null hypothesis is true, okay, but we reject the null hypothesis, even when it's true. So that is called a type 1 error. So that is a probability. So type 1 error is basically the probability of committing what? Is basically the type 1 error is basically the probability of rejecting the null hypothesis when it is true. And there are also instances where the null hypothesis was false, but we failed to reject the null hypothesis, even when it was false. Okay, and that actually introduces us to something called a type 2 error. Often the type 2 error is represented statistically as a beta, and the type 1 error is often represented as an alpha in most instances. Yeah, so that is one thing we have to note. So now, so it means that these are two errors, okay, and we don't want to have such errors in the process of performing our experiment. So it means that we need to find a ways and means to control these errors, especially in terms of its magnitude. So the whole essence of sample size determination is this: if your sample size is too large, okay, and remember, so when I said type 2 error is the probability of failing to reject the null hypothesis, even when it is what? False. So it means the probability of making that correct conclusion, that is rejecting the null hypothesis when it is indeed what? False, is basically what we call power of the test. So power of the test is just a probability. Okay, so it's just a probability of not committing type 2 error. Okay, and that is something very important, because most of the time we are doing an experiment to determine whether we can detect a true effect. Okay, so the ability to be able to detect such effect is what we also mean as power. So it means in every study that's the goal. Okay, right, but remember, it's the null hypothesis we test, not the alternative. So the null hypothesis is that there's no effect. So that is what we are trying to check, whether it is true or not, so that if there's an effect, then that is, if we reject the null hypothesis, then we conclude that there's an effect, and so on and so forth. So now, why do we have to estimate the right sample size? So if the sample size is too large, what happens is that it increases the power, and by so doing, it means that even when there is no effect, okay, or if an effect exists and is so tiny, with a large sample size, we are still able to detect such an effect. And sometimes what happens is that even the detected effect could be due to random chance. Okay, so that is one of the things that using a very large sample size also result in. So by so doing, large sample size, if you think about it, even when there shouldn't have been an effect, because of the large sample size, we're able to detect an effect. So by so doing, it means that with large sample size, we tend to increase the chance of committing type 1 error. So if you remember, I said type 1 error is the probability of rejecting the null hypothesis when it is true. Okay, in other words, it's a probability of concluding that there's an effect when there's no effect. Okay, when I say when there's no effect, when there's no true effect. Okay, and then when your sample size is too small, this is what happens. So when your sample size is too small, even when an effect exists, we are not able to detect it if the sample size is too small. Okay, so by so doing, with small sample size, we tend to increase our chance of committing type 2 error. So remember, type 2 error is the probability of what? The probability of failing to reject the null hypothesis when it is what? When it is false. Okay, so it means, in other words, type 2 error, you can think about type 2 error as so if you say failing to reject an hypothesis, that is concluding that there's no effect even when an effect exists. Okay, so it means for small sample size, when very small sample size, when a true effect exists, we are likely to increase the chance of not able to detect such effect even when it exists. Okay, so that is the whole essence of why we need to always achieve and compute or determine the minimum sample size that is able to control for these kind of errors associated with our hypothesis testing. So in view of that, it means to determine sample size, we have to sometimes predefine the power we want to achieve, predefine the error rate, and the error rate, specifically the type 1 error rate, we often, or in this case, we just say the alpha error rate. We often set it at 5% for most studies. And remember, if it is 5%, in most studies for a one-sided test. The moment you consider a two-sided test, for one-sided test, that is if you are testing whether the effect is greater in some group than the other, or less than in some group than the other, then that one is a one-sided test or a one-tail test. And in that case, your alpha is not divided by 2. So that is, if you are sticking to 5%, you work with 5%. And situations where you want to conduct a two-sided or a two-tail test, in essence, you are trying to test whether there's effect or not. You are not interested in the direction of what the effect, whether it's less or higher in some group compared to some other groups, or and so on. So in that case, you divide the alpha by 2. So remember, we always divide the alpha or the alpha error rate, okay, or the type 1 error rate. We always divide that by 2 for a two-tail or a two-sided test. And then for a one-sided test, we do not divide. And remember, when you are doing or determining the sample size with the GPower software, you need to take this into account. One will say that what is the problem when the error rate, okay, so for instance, when your alpha error rate, you are doing a two-sided test, but you fail to divide by 2. So what happens is that, first of all, it kind of compromises on significance. By significance, it means situations where the effect wasn't supposed to be significant. Okay, it makes it a bit less stringent in terms of significance, such that even when the effect wasn't supposed to be significant, it tends to become significant, or because you didn't control for the error rate to suit the kind of test you are doing, whether you are doing a two-sided test or a one-sided test. So that is one thing that we need to take, that we need to consider. So one of the key thing is the fact that it kind of compromises upon our significance criteria, and in view of that, it questions even your research findings and its credibility. So remember to control for make sure that if we are predefining, because remember, when you're trying to do the sample size determination, we would have to predefine some parameters. And the parameters we often predefine, irrespective of the kind of statistical analysis we are going to do, we are going to predefine our alpha or our type 1 error rate. Okay, it is mostly 5% for a one-sided test or a one-tail test. And then you rather divide the 5% by 2, that is 2.5%, if you are considering a two-sided test or a two-tail test. Okay, so that is one thing. And you have to predefine your power. Most studies assume at least 80% power. Okay, if the power is at least 80%, then it meant that your type 2 error, that is your beta, was 20% or 0.2. So these are something we predefine. And one of the most important thing is the effect size. Okay, so we were talking about effect. So one thing, if you watch the introductory section where we describe the entire scope of the subsequent lecture series that we are going to have. So one thing that we touched on was that, depending on the complexity of the experiments, for instance, those who are into clinical trials, okay. So for instance, those who are into clinical trials, especially concerning adaptive trials, where sample size could be recomputed in the course of the study, where the study could be stopped earlier or terminated early for either futility or safety or efficacy, and so on and so forth. It means that, or even studies where over time there's going to be some interim analysis, for instance, group sequential designs and so on. It means that the sample size is determined to capture these dynamics in such setting. And then there are also other settings where the design is not as complex as in these adaptive designs, like group sequential designs and, let's say, other platform designs and so on and so forth, which can be very complex in terms of its structure. Okay, so it means that in most cases, especially in clinical trials, we estimate the sample size to capture the design of the study. Okay, and for those or for those of us or most people who are also doing other experiments, it could be animal experiment, or it could be a trial on humans and so on and so forth. One thing we have to notice, even in determining the sample size, apart from what I've already discussed on controlling the type 1 and type 2 error, depending on how large or small it is, you know that if we know that we need this minimal number of samples or individuals to perform our experiment to detect an effect, and you use more than that, okay, depending on the experiment, it could even go against ethical concerns. Okay, so this is why it is always imperative. To determine the minimum sample size that is sufficient enough to detect an effect if it truly exists. And one thing is that the effect size is computed based on the data. So in most studies, let's say you are trying to do a new study or a new experiment, but you previously have done some preliminary analysis, or from literature, there's already, previously published results or data in the literature. You could inform your effect size based on those previous literature or a preliminary analysis or a preliminary data that you already have, okay, concerning something similar to the study you are trying to do. Okay, so the effect size is always computed based on, in the case of less complex designs, the effect size is often computed based on the primary endpoints. Okay, so what I mean by the primary endpoint is what is the main outcome that you are trying to investigate, or what's the main outcome that you are trying to check whether it differs between some comparable groups or not. Okay, so the primary outcome, whether it is continuous, whether it is discrete, whether it is skewed, or whether it is non-normal or normally distributed based on the preliminary data, would inform the kind of analysis you could do. So remember, we know that anytime we have our data being normally distributed, we can always use parametric methods even in the process of performing statistical analysis. And during departures from normality, we often go for non-parametric methods, right? But there are instances we have certain kind of data, especially data measuring antibody concentrations, data measuring, let's say, GAG protein responses and so on. We know that such data sets are often naturally right-skewed, for instance. So it means that they are often skewed in some sense. So it means if we wanted to power such a study, though most of these data are skewed based on the original data, but after taking log transformation of such data set, it becomes normally distributed. So in essence, such data set, for instance, antibody concentration, let's say GAG protein responses, and most outcomes, okay, especially when we deal with immune kind of immune response studies and so on and so forth, most of these outcomes are often right-skewed, but they are log normally distributed. By essence, the original data is not normally distributed, but its log transformation becomes normally distributed. So it means that in such setting, it will be imperative to determine the sample size based on the log transform. Okay, and if you are doing it based on the log transform, then it means that you are going to use a parametric test in order to what? To estimate the effect size. Okay, so that is one thing we have to note. So often the effect size is obtained based on the kind of primary analysis that you're going to do on that primary outcome. Okay, so that determines that. But situations where from the preliminary data, you even realize that even the log transformation or any other appropriate transformation didn't make the data normally distributed. So when it happens that way, then it means that the only thing to do is to obviously use a non-parametric method, right? I've already covered a lot of these statistical stuff as to when to use non-parametric, when to use parametric, when to use univariate, multivariate analysis, and so on and so forth on my YouTube channel. So feel free and watch all those videos. You can always revisit, and don't forget to subscribe to the channel if you're new to it. By your subscription, it helps the videos to reach out to many people. So please help us with that. To continue from where I left off. So basically the effect size is computed as a function of the primary analysis you are going to do on that primary endpoint or primary outcome. Okay. And so, but there are instances where after every or all forms of data transformation, it doesn't help achieve normality. So it means using parametric method for such analysis or to even determine the effect size based on the parametric methods becomes questionable, even because you know that the data couldn't achieve normality even after transformation, and also before and after transformation, or even after using Box-Cox transformation and other complex transformation, including maybe ordered quantile normalization and so on and so forth. Still, you didn't achieve normalization after log transform and so on. So in that case, then you have to power your study based on a non-parametric test. So it means that for such instances, you're obviously going to use a non-parametric method to compare medians rather than the means, because we know that means are affected by what? Outliers, or when in situations where data is non-normal, then it means that comparing means could be an issue. But remember, it's not always that non-normality is due to outliers. There are instances it's also due to skewness. So a data could be non-normal, not because there were outliers. A data could be non-normal because it was skewed. Okay, but remember, a data is said to be an outlier if it falls outside 3 standard deviations of the mean. Okay, so it means that there are instances where the distribution is most of the bulk of the distribution is centered maybe 3 standard deviation above the mean, so it's skewed to the right, but it doesn't make any of the observations an outlier. So this is something, I mean it's not related to this. I just chipped it in. All right, so it means situations where the primary endpoint before and even after data transformation cannot be normally distributed. So then in that case, you have to power your study using the appropriate non-parametric method. And with the help of the GPower software, we are going to learn how to perform appropriate power analysis and to determine the minimal sample size based on the primary analysis, whether you're going to use a t-test by t-test, whether you are going to work with a comparison between a dependent group that is a pair t-test or 2 independent group that is an independent t-test, or and so on and so forth. And then we'll look at ANOVA type models, situations where the comparable groups are more than 2, and there is even situations where the measured outcome was recorded at multiple time points. That is a repeated measures ANOVA. And so in that case, we will look at the case of 8 parametric and non-parametric version. And we'll also look at situations where you are not only measuring one primary outcome. Okay, the goal is not just to look at the effect of just one primary outcome, okay, between or across or within a certain group, but the goal is you are measuring several outcomes at the same time, and the goal is to compare whether that vector of outcomes or group of outcome or primary outcomes differ significantly between some comparable groups or not. So in that case, then it becomes imperative to do a multivariate analysis. Okay, so it means in such instances, it's better to power your study using an appropriate multivariate method in order to power such study, rather than powering the study based on each primary outcome separately, which is inappropriate. So this implies that with the help of the GPower software, we are able to power our study based on any primary analysis we seek to achieve, okay? And by so doing, remember, we need to know the effect size. And computing the effect size, each primary analysis, whether t-test, whether it's a pair t-test, whether it's an independent t-test, whether it's an ANOVA, one-way ANOVA, whether it's a two-way ANOVA, whether it's a regression analysis, whether it's a multivariate ANOVA, whether it is a Hotelling t-square, that is a multivariate t-test, we need to be able to, the effect size is obtained differently. Okay, so we are going to learn how to detect the effect size also from the GPower software directly without having to calculate it externally elsewhere before using the software. So without wasting much time, we are going to start on how to use the GPower software for our first lecture series. So this is just an intro to the first lecture series, and then we are going to start we are going to now switch to the GPower software and learn how to do some power analysis, sample size determination, and so on and so forth. So stay tuned, and please don't forget to subscribe to the channel and watch the previous videos, knowing especially the entire scope of the study. I have extensively talked about these on my on the first video, introductory video on the scope of these lecture series. That's where I went extensively, even how to, we talked about even when your study would investigate into complex relationships using, let's say, structural equation model. So it means that when you are now determining the minimum sample size, the effect size should be computed based on the structural equation model, and so on and so forth. If it's a regression you're going to use for your primary analysis, then it means that you ought to determine do the power analysis based on that regression. If you are going to include interaction, account for anything, you can actually include all these things in your power analysis, so that you don't use a different software. So you don't power your study based on a different primary analysis or based on a different statistical analysis, only to use another or different statistical analysis after you collect your data. So in that case, then it means that you could end up underpowering your study one way or the other. So this is one thing I want you to know. So without wasting much time, I will end here, and then we will switch to using the GPower software in the next video. Thank you very much.